So welcome everybody to this very special lecture of Professor Jason Speyer, whom I guess most of us know, but for those few who really need this introduction, I will say a few words, and we can't just do without it. So Professor Speyer got his BS in Aero and Astro from MIT in 1960, and then he received his PhD in applied math from Harvard University. He then worked several years in the industry, which convinced him that industry is nice, but academia is better.
That's right.
So he had lots of experience in the industry, and that's important. But then he went on to assume an academia position at the University of Texas, Austin, where he was a chair professor from 76 to 90. And then from 1990 to present, he's a distinguished professor in UCLA. Professor Speyer is well decorated. He has many awards and prizes. I will just cite a few. He has a fellow rank in both the American Institute of Aeronautics and Astronautics, the IAA, and the IEEE, the Institute of Electrical and Electronics Engineers. He has the two most prestigious awards of the IAA in the control area, which are the Mechanics of Flight Award and the Aerospace Guidance, Navigation and Control, the GNC Award, which he received just in 2012, I believe. And he has the IEEE Millennium Award, and he is a member of the National Academy of Engineering and other awards. Professor Speyer has written 3 books, and he has a list of hundreds of papers. And he has, I need to say a few words about his relations also here. I remember him from 1983, and that was not the first time that he was here. He spent sabbaticals at the Technion in the University of Ben Gurion, Ben Gurion University in the Negev, and the Weizmann Institute. He is a personal friend of many faculty at the Technion, in BGU, Tel Aviv University, Weizmann Institute. His son lives here, and recently, I think for the last, 6 years, Moshe, he's in touch with Moshe Idan, our Moshe Idan. Both of them have the BSF award, and they tightly collaborate on exotic estimation problems.
I wouldn't go that far, exotic.
Okay. So, one afternoon I was sitting and I had nothing to do, so I was looking at Jason's CV, and I saw that he has a BS from MIT and a PhD from Harvard, and I thought that something is missing there. So what's missing there? Huh?
Never heard about those institutions.
Something is missing there. He's missing a doctorate from the Technion. So, right, you see MIT and Harvard, so Technion is missing. And so who wouldn't like here a student like Jason Speyer for a PhD, right? So right on, I called him, and he agreed. And submitting him for the Doctor Honoris Causa of the Technion, the Honorary Doctorate, was a piece of cake. And I guess, although I was not there, that honoring him with the degree was also a piece of cake for them, for the committee. And he indeed received the award in a very exciting ceremony which took place on last Monday. Just to show you why I think it was easy to honor him with this degree, let me read a few words from one of the letters. And I don't believe that Jason knows that people think about him like that. So, the decade of Apollo and the pioneering period of manned spaceflight owe its successes to the ability of engineers to understand and apply the relatively new concepts and methods of feedback control. Unmanned spaceflight requires even more reliance on feedback control. During these early developments, where propulsion, aerodynamics, astrodynamics, and control theory had to be integrated before even modest success could be achieved, there probably doesn't exist a greater leadership enabling these events than Speyer and Draper. Feedback control theory developed rapidly in the 60s and 70s, but even NASA was reluctant to use what was called at the time modern control theory. A famous quote from a NASA official at the time: "We have not used modern control theory in any spacecraft, and we do not plan to do so." But partly due to Speyer's leadership in both theory and practice, he helped NASA change its mind and open the door for decades of even more increasing performance capabilities of spacecraft and aircraft. In fact, Speyer has been a good ambassador to the world to educate about the powers of systems and control theory in modern life. Speyer has always been an innovator. He was a leader in theoretical pursuits as well as applied ones. He was first in several control trends: H-infinity control, decentralized control, game theory, singular optimal control, and periodic control. Not content to be an innovator in mathematical theory, he also was the first to solve important aircraft and spacecraft control problems. He changed the way cruise is done in high-performance aircraft. He changed the way navigation was done in every Apollo mission since Apollo 8. He changed the way Patriot and other guided missiles do their guidance. He introduced modern control theory into Air Force aircraft, beginning with the F-16, the AFTI F-16, and the F-18 Howard. The Speyer filter was used by the Ballistic Missile Defense Agency. He provided fault detection algorithms for the PATH program of Caltrans. His fluid control work reduced drag by 18% in turbulent flow, and on and on. So this gives you just, the gist. With this, I would like to welcome Jason Speyer to give his talk.
Thank you, Echo. Thank you. That's more than I could have imagined, actually. Actually, one of the things has happened because I got this doctorate degree is that it changed the way I talk about my education. Before this, I had all of my education north of the Charles River.
And now it's south.
So now I get a little bit east of the Charles River. Well, thank you so much. And so thank you so much for being here. So let me, with the few minutes that I have left, let me talk about a system theoretic approach to the control of channel flow. This is work that I did. A lot of this work is done with John Kim, who's at UCLA, and people also at UCLA, which was Arthur Orr and Luca Cautalese and Sun Kang and others that have been involved with this over the years. This started actually with Sanjay Joshi and along with John Kim in the idea of, can we apply system theoretic ideas to flow control and basically feedback for these kinds of systems. So what I want to do is talk about basically finite state system approximations that we started working with, and in particular reduced order models for non-normal dynamical systems, which is associated with the Navier-Stokes equations, and then look at some things that we did in the control of turbulence, and then finally talk about upstream, that's a little bit quicker than I wanted to, talk about upstream traveling waves and friction drag, and the fact that these things basically lead to instabilities due to these upstream traveling waves. They lead to possibly periodic controllers and the little tricks that we did to solve this class of problems. From a controls point of view, this was insightful. Maybe from the fluids point of view, it seems maybe somewhat mundane. So it just shows the variations between what one looks at and in terms of what you think is important and what you think is insightful. So let me just sort of start out with talking about the models that we're using, which is basically Purcell flow, which is subject to basically pumping and suction as the control input, and shear stress measurements as the output at a wall. So we're talking about flow. We'll talk about it either in 2 dimensions or 3 dimensions. Here I'm going to talk about it in 2 dimensions. It's simpler to describe. And so we have I didn't mean to do that. We have a perturbation field V, which is made up of basically 3 directions, U streamwise. Then this would be maybe small v going span-wise, and W being vertical. So one is looking at these things that one looks at a complex stream function in this form where U is the partial of phi with respect to Z. Z is in the goes along the height of the channel, and X is along the channel, and so therefore, and W therefore is the velocity perpendicular to the wall. So these are the 2 velocities that we're going to consider, and so we'll look at the partial differential equation for the Orr-Sommerfeld equations, which are basically this operator eta operating on the partial of phi with respect to t of phi, plus an operator on phi itself, and these this partial differential equation basically at the wall at -1. Which is at the vertical part of the wall at -1, we have the control U, which is what is giving us this pumping action. And other than that, everything else is 0. So we have a 0 slip condition along the wall. And these particular operators, which you probably know well, are given by these partial derivatives with respect to Z. The K comes from assuming a Fourier decomposition of this partial differential equation associated with X that goes streamwise, and L basically is, again, this type of operator on this. And this is the kind of thing that we want to decompose. So before we can do that, let me just sort of describe this as Purcell flow. This is the center, this is the velocity streamwise associated with the height. So at Z equal to -1, this is 0, and then the center of velocity is at its greatest value when Z is equal to 0. And again, RE is the Reynolds number. The other part of this is that we're going to talk about shear stress, and shear stress is basically given again along the wall by denoted by Y of t, and S is an operator operating on, again, the stream function. So you can look at some of these operators as, in a sense, being invertible, and then you get a structure which basically can be decomposed. And this is the decomposition that we're going to look at and basically focus on. So the notion really here is that the stream function, which I've written here only in terms of Z and T, is basically a sum of independent or orthogonal functions. In this particular case, we usually use Chebyshev polynomials. It's not necessarily the only ones to use, but we've used those. But the other part is that the time behavior is captured by this coefficient. And these coefficients are the ones that we look at in order to construct our state space models. So when you look at an element of the state vector x, it's going to be one of these. So this guy over here is for a particular wave number k, and it's the mth element of this particular sum, and all of these from 0 to m is going to form a state space. So this is what we're going to use in order to construct our state space, talk about a input-output relationship relating, for example, this is the output, and it's a function of t. This will be a state space associated with the time, and then there'll be an input with respect to time. So these are the kinds of things that we're going to operate on. Okay, so the spectral techniques that people have been looking at, for example, two of which are pretty popular, is the Galerkin method and the Tal method. And the object here is that they may give different results. So that's, they actually don't, but I wanted to make a statement about what they do look like. So both the Galerkin method and the Tal method employ the same type of basis functions. The Chebyshev polynomials form a orthonormal set. The basic differences of these two states arise in the way you incorporate the basic control action. In one case, you do it by redefining the stream function so that the boundary conditions are all 0, but the forcing term is in the partial differential equation. The other method basically handles it directly, which is the Tal method. So, so the Galerkin method makes the change in the stream function so that the boundary conditions are homogeneous, and the Tal method handles it directly. They should give the same answers, and we'll take a look at that. So the idea of all this is first come up with a state space with a high order, then let's reduce the state space, see what that means in terms of what you lose when you have an input-output structure, and then use this in order to form controllers in order to reduce turbulence. So the state space representation for this input-output structure is basically using these two spectral techniques are going to give a structure that looks like this. So it's going to be an nth order. We're going to, you would take these sums to infinity, but you've got to cut it off at a reasonable number. Sometimes this number is pretty big, so the state space is pretty large. Here we have x, which is basically composed of all those coefficients. A that we were talking about, u is the input, y is the output, and it may have a direct throughput, u. And so, and one of the things that is a little bit, maybe I don't want to make it disconcerting, for some people, there's going to be complex matrices, like A will be a complex matrix, and here U will be a complex matrix. Or we can make a transformation from an n-dimensional system to a 2n-dimensional system where everything is real. Okay, so, and people who, half this room is filled with control people and half this room is filled with fluids people, and I think it, so we'll just look at these things as A's, B's, and C's because you get the same type of answers either way. So in compact notation, you have an A, B, C, D structure, or it could be that D is equal to 0. So what happens is the following. This feed-through feature basically turns out to be unequal to 0 in the Galerkin method and equal to 0 in the Tal method. And so what is the relationship between the two? It turns out that in the tau method, there are always two very fast eigenvalues. And if you allow that to go into steady state, then what you do is you basically recover the same D that you get in the Galerkin method. So these methods are completely the same. Okay, so after doing all that, we looked at different stages of this work. So what we wanted to do is take a look at the following. What I want to do is look at metrics for these systems, because now that we have a large dynamical system, even though we've reduced it from being infinite to finite dimensional, it's still very big. So some of these things may be 130 states, for example. What we want to do is create metrics that when we reduce the structure from maybe 130 to maybe about 20, what do you have left? What happens when you use reduced order models like balanced truncation to these kinds of structures? So the first thing I want to do is talk about these metrics. So the two of them are this resolvent, which is basically just looking at the effect of the inverse of Zi minus A, and where Z is a complex number, or the transfer function, which uses Z but has an input-output structure that it's associated with it, C being the output matrix, B being the input matrix. And so so one of the things we might look at is the norm of RZ, which is abbreviated by in this way, which is the largest singular value of RZ. And so we'll plot this sort of thing. So we're going to look at, for example, the spectrum of the frequency response of the resolvent norm of the operator A, which is this. And we're also going to look at the frequency response of G of Z. And we're going to make a comparison between these two. And we're going to see what they do, what they look like for the full state problem and for the reduced state problem. Likewise, we're going to do that for the frequency response for G of Z, and we're also going to look at the pseudo spectrum by looking. Whoops, well that was fast, wasn't it? By looking at something of the sort. We're going to look at R for all values of Z in the complex plane. And we're going to look at contours of this function for various values of epsilon. So we're going to look at this because this pseudo spectrum is what a lot of people have looked at as one of the guides towards what creates turbulence. For example, it may be a stable system, but the transient response may throw it into nonlinear regions for which it now becomes turbulent flow. So that's so that's one of the things we'll be looking at. What does feedback do to that underlying structure? So let's take a look at reduced order models. And the usual thing in the controls area is that you look at what's observable and what's controllable. So what we have here is an observability Gramian, WC. That's a controllability Gramian, WC, and observability Gramian, W0. These basically, the structures of these things tells us which is most observable. So what we want to do is construct a system which is most observable and most controllable. You could have a system that's very controllable, but you can't see it. Or you can have a system that you can see very well, but you can't control it. So you want to balance those two things together. And it turns out that there is a similarity transformation T, and S is the inverse of that, where you can decompose WC, and you can decompose WO, which is the observability Gramian, which gives you a sigma, which is basically the singular values that are associated with both of these guys. And these guys are ordered. So you've got one transformation which basically gives you an ordered set of singular values, and you use those basically, these are called the Hankel singular values, and you order them in descending orders. And these Hankel singular values provide a metric for ordering the most controllable and observable modes according to their energy content.
Jason, do they have to be identical values like that?
Yeah, they are identical. Yeah, they're identical. Within this transformation, they're identical. And this is where you get balancing, because you balance it with this one transformation, you balance the most controllable and observable eigenvalues by doing that. And then you use them basically by making the following reduced order system. So NR is much less than nth order, okay? So what I've got here is an nth order system, and I'm throwing away a lot of these dynamics, and where AR is given by these similarity, by these well, this is a similarity transformation here. But these guys over here are, so S1 and T1 basically are the nth rows of S or the columns of associated with T in order to make this transformation. So you might start out with 130 states, and this guy over here may have 20 or less. But they're balanced between the most observable and the most controllable structures using this particular transformation.
Can you estimate how much energy is lost by this truncation?
You can look at the errors that are associated with this, with the truncation, and get an idea of what you've lost by doing that. There's a norm associated with the structures. A guy called Eanes basically showed what that value was. So you can bound it by a norm. Okay, so let's take a look at some of the structures. This is so if I look at the full order system, you get a structure that looks like this. This is the imaginary axis, and this is the real axis here. And so you get a structure that looks like this. You get this kind of interesting Y form. The X's basically along here are all the poles of the system. The zeros here the zeros here are zeros. And zeros are structured from the input-output relationships. So this is what you get from an input-output relationship, where you see a lot of zeros on top of poles. They're almost canceling out in a certain sense. Okay, so this is what you get from this kind of a structure.
This is after the reduction? This is the reduced model already?
No, not yet. No, let me go back. No, this is the full order system. Yeah, and I haven't got all of them here. This Y goes all the way out like that.
I didn't count them, so I didn't know.
Why are you so slow today? Did you ever see so many zeros? Okay, so, and actually it turns out that we found a zero that's up there as well. If you then reduce the system, then you don't even, these pole zero structures, the pole zero structure near the imaginary axis is pretty much retained. But you've lost all of the stuff that's over here. So this becomes your reduced order model. Quite different. But you're not quite sure what it means yet. Okay, so let's take a look at the frequency responses of the resolvent that we talked about before as a function of omega, and the transfer function. And this is for the full order system. And basically this is the resolvent, the blue line, and this is the transfer, this is for the norm of the transfer matrix, which is pretty flat out here. And this is probably due to the zero in here, and it goes off like this. Now, this part over here, you can see that there's a huge difference between the amplitude of these two different structures due to the input-output relationship. Makes a big difference. When you go to the reduced order system, you can see that the resolvent structure over here becomes much reduced than this one. But what you see over here is what rather interesting is the transfer function doesn't change at all. The transfer function remains about the same. So that's one aspect of it. If we look at the pseudospectrum, which Fowler and Tunisian. Is it Tunisian? Can I spell? Am I saying it right? Tunisian. All of these people had looked at these kinds of pseudo-spectrums and basically hypothesized that these were the kinds of things that drove things into possibly into turbulence. So you see these are all lines of constant resolvent as you move up along here in this structure, and it's pretty full. You can see that it's pretty full everywhere. If you go to the reduced order system, you see that it becomes far more sparse than what you have here. And you sort of lose all of that structure that was in terms of input-output relationships, or when you reduce the system, you lose all of that structure that you had over here. So you're not reproducing it in this particular way. Okay, so you lose that kind of structure. So the basic point then is that, well, the basic point I want to make is that when you reduce the system, you lose a lot of the structure that may be happening in the flow field because you're only looking along the wall. And you're only being able to control along the wall. So the input-output relationship really does make a significant difference in the possible capability of your controller. And that's what this is basically trying to tell us. So, but nevertheless, so what we've done is, still we created three-dimensional controllers for this structure. Let me show you what we did. So this becomes the channel, and I hate to tell you that. Now Y is in the vertical direction. Z now is span-wise, and X, fortunately, is still stream-wise in this. And so the little blue things over here are sensors, but the notion here is that the sensors are continuous and the actuators are continuous, okay? And they're usually Fourier in structure. So what you're doing is you're taking the information of these sensors, you're putting that into a fast Fourier transform, and what that does goes into each of these are associated with a particular wave number. So what we're controlling out of this whole bank over here are a whole set of wave number pairs. So that's what this structure over here means. This all comes back into a fast Fourier inverse Fourier transform, and then we actuate along the wall. So this is the kind of structure that we're dictating, and this is the kind of structure that I'm talking about for any of the controllers that I'm going to be using. So
when you jump to 3D, your basic equations, no, about it. The stream function.
Oh no, you can't use the stream function anymore, but you can still, have a linearization of the Navier-Stokes equations. And that's what we use. Yeah, the stream function was a simpler way of just sort of getting started. Yeah.
Also, you switch from CISO to MIMO. This is multiple output.
Huh?
It's not a CISO, single input, single output system.
Well, even in the two-dimensional case, there are really two inputs. The two inputs are basically the real and imaginary part of the control, and the two outputs are also that form too. So when I show you the transfer function matrix, that's what I meant by the matrix. I took the norm associated with that, and that's what I plotted. So
you have many sensors and many actuators.
Oh yeah, yeah. Oh yeah. If you meant that, the fact is, this is a huge number of this could be a large number of structures. The question is, how do you reduce these? You want to reduce these in two different ways. How many of these do you actually need to control the fluid? And the question is, this is an estimator and this is a controller over here, and you've got to make a whole bunch of all of these. That's an awful lot of states unless you do model reduction. So the kinds of notions of doing model reduction are embedded basically in the way we form these. Okay, so the control is designed to reduce viscous friction drag, and the wall shear sensors feedback to the actuators distributed along the bottom wall as I have here. And the control is only applied to the perturbations indirectly to the mean flow field. And basically, it's sort of indirect to drag, the way this is. So what you want to do is control the fluctuations in every one of the wave numbers. Hopefully, if you do that, you will then get reduction in drag. Okay, so so basically, what I'm saying is that the spectral decomposition allows us to break this thing into wave number pairs. Okay, so, and the controller we used is the linear quadratic Gaussian controller with loop transfer recovery. It's probably well known, and we could use H infinity if we wanted to in this case. Okay, so so friction drag is represented by the wall shear, okay, and that's what I'm going to show here is the reduction in wall shear. So what I have here is a picture. First, so along here is wall shear, along here is time. This black line over here is if you do nothing. And we used a couple of controllers. One we called it was a ad hoc scheme where we used two-dimensional controllers sort of lined up along span-wise along the channel. Okay, and that's what the blue line is. And then we used a full 3D controller. They basically reduce drag about the same between the two, but basically if you looked at the power, yeah, that's a good question. It's not very large. Maybe about, I would say most of this is about 5,000.
Based on the channel video,
huh?
What is the characteristic length that you use in that number?
That I've forgotten what we use. Huh?
Channel halfway.
Yeah. But the Reynolds numbers, I think, were about 5,000. I mean, you can't go any higher than 10,000 because this was all done in a nonlinear direct numerical simulation.
The transition is completely different above 5,000 and below 5,000. Above it, its small disturbances can be amplified by linear process, and below that, you need the transient growth.
Yeah, right. I think that this was, I don't remember precisely. I got to take a look at the, I can look at my phone, but I think that this was below 5,000. This is below 5,000. So this was, and this flow field was already stimulated, but not by a small perturbation away from the laminar flow, but basically it was already done, and this was the result. So this was started way out. All of a sudden we turned the controller on about here, and this is what we got from the controller.
What about the low scale? Just stop and tell you what it is.
This one over here, the blue line over here, this is VW, which is effectively the power associated with the norm of this is effectively the power that's being used in order to control these to control the flow. The blue one over here, basically you can see is twice as large as the red one associated with the three-dimensional flow. So we were doing better in the amount of power that we were using. And what we effectively got was somewhere between 17 and 19% drag reduction for that sort of thing. Okay. So another place to look, though, is that when we did this, when we were getting these results, what we did is we started looking at the transient performance of these controllers. And basically the notion was the following. In a two-dimensional flow, we got these huge transients well below laminar flow. And then they popped up like this. And then in three-dimensional flow, not quite as strong as this, but we got basically the same kind of dip in the drag along here, which gave us the notion that maybe one could do is could have an oscillation associated with this, and you could sustain drag below below the usual laminar flow field. So that was the idea of this kind of looking at this. So this is the direction we started looking at. But that was not particularly easy. So but it turned out that we could look at some results which may be associated with the total drag, where DL is the laminar drag, and this guy over here is the Reynolds shear stress associated with the total drag. So this guy, if we could make this piece over here negative, it may be that we could sustain laminar flow below, we could sustain a flow field below laminar drag. Okay, so that was the notion. So the conjecture by Bewley was basically that couldn't be done. You could not sustain drag below laminar flow because he couldn't find an oscillation which would sustain it. Okay, so but it turned out that that the transients of the flow controller indicate that this may not be true, and the integral of the Reynolds shear stress may be made negative. And what we determined is that if we use an upstream traveling wave, not downstream, but upstream traveling wave, we could reduce the drag. So in trying to find a periodic flow, it was discovered that what we could do is use a flow of this type, but this C of K was negative instead of positive, and the flow was going upstream rather than downstream. So this A of K is an amplitude of a given number. This is a particular wave number, and multiplying this by this cosine function. Okay, so the drag reduction did result in a favorable Reynolds shear stress, and below that we were able to capture both below laminar flow behavior was captured in both linear and nonlinear regimes. So the linear equations demonstrated, which was interesting. We could talk about this in terms of drag in a linear structure with this upstream traveling wave. And that's what we have basically along here. Here we're plotted Reynolds shear stress from minus 0.5 to 0.5. And you can see that this dashed line is for a downstream traveling wave. So we increase the amount of drag by that. And the blue line is positive here, and we decrease the amount of drag. Here we also see the effect of wave speed on this structure. And so over here you can see that when we have a downstream traveling wave, we get really high peaks in the amount of drag. But over here, you can see that what we're getting is a significant reduction in these numbers are somewhere they should be negative. I guess that didn't capture it very well, did it? This is 0, and these are negative numbers, and this should be somewhere in here, huh?
0 is not at the lowest point.
Yeah, zero isn't, should be.
No, it is.
Huh? Have I got that looking wrong or what? Because this definitely is.
The bigger figure ends at -1, and here you're showing us -2 in wave speed.
Yeah, but it starts here at -5.
The size is 100.
No, the size is
100.
It's 0.
-2.
Well, anyhow, I believe this one over here and take that as it is. Okay, so the point is that, well, it seems like that can happen. And not only that, I mean, maybe this is a better figure. So here we have basically amplitude for a particular, this is all for a upstream traveling wave. And the solid blue line is the linear prediction, and the little red dots are what comes out of the direct numerical simulations. Okay, so which shows that you're not doing too badly predicting with this linear structure. It kind of goes off a bit over there. Over here we have basically the 2D structure, which is nice and stable. But over here, and this is the new, if we started it even here, but not with but with a flow field that is allows it to be largely perturbed away from the structure over here, you find that this actually pops up and then goes into the same structure as over here. So there's an equilibrium here, and there may be an unstable equilibrium over here. So you have two equilibriums associated with this structure. This one is a turbulent layer, but what's interesting about it is just using an upstream traveling wave, you actually reduce drag, okay, in the turbulent flow field. So that's the basic point here is, one, it's unstable away from this value, which is below laminar flow. It travels up, becomes turbulent, but far below the turbulent mean that you would get over here. So that's so this is the thing that we're going to kind of focus on. And in particular, what I want to finally focus on is the notion that if you start very close with a small perturbation away from the two-dimensional flow, it takes some time before you have an instability, but you do have an instability that brings this basically up to into this structure, and I do have the Reynolds number over here.
Did you try to estimate how far it is in physical distance before it starts giving you this advantage? Say 300 in your time units. How much would that be in physical space and distance?
Oh, I mean, yeah, I mean, how far down the channel would it go?
Yeah.
I don't know. I don't remember any of the dimensions.
That would say how many times you need to do it.
You mean, well, I mean,
You start your process.
yeah,
It takes some time for the drag to go down.
Yeah.
500 or so in your units, but the flow has moved forwards meanwhile. So how far is it?
yeah, but the assumption is the traveling wave is almost in steady state all the way along this path.
But it takes time, right?
Yeah, it takes time. The traveling wave is operating all the time. I start out here with a small perturbation away from at this point. And so this is the perturbation away. And then it takes a certain amount of time. You're saying, well, how far where did the instability basically occur along the channel? Yeah, but I don't know the answer to that. Okay, so so basically the idea, though, what I want to do is talk about how do I control the periodic feedback control of these instabilities. And that's what I want to end up with. So the traveling wave induces these instabilities in the three-dimensional channel flow, and you can basically find these structures or these instabilities by using flow K theory. But the trouble with flow K theory is that you can't use it for control, unfortunately. So these equations predict the introduction of these instabilities for small amplitude traveling waves, but they do not provide the proper framework for this. So the essential observation, which is maybe not a great one, but the dynamics of the steady state flow induced by the traveling wave must be linearized and decomposed in a reference frame moving with the traveling wave. So that's what we do. Okay, so so the resulting linear time this results in linear time invariant equations. So what happens if you are at if you're watching this thing in a static frame, it's oscillating up and down. So you need a periodic controller in order to do that. Those are very difficult to get to. But if you go along the traveling wave, you basically can then create a time invariant controller. That's the good news. But you still have, when you define the linearized equations, it turns out that the wave numbers streamwise are coupled. So you get a very large dynamical system that's associated with it. That you're stuck with no matter if it's in a moving frame or in a static frame or not. Okay, so what we looked at is consider this traveling wave. We assume a superposition of the traveling wave flow on the base flow. So this thing looks like the following. This is the base flow. This is the velocity due to the traveling wave, and this is a perturbation associated with it. So these are in three dimensions. And C indicates the traveling wave. All the velocities are normalized around the center line, and what we do is we get a traveling wave induced by this structure over here. So the question really is that how do I produce V prime? Okay, so the point really is I get a structure like this for this by introducing the traveling wave into the linearized dynamics at each wave number pair. So you put a periodic structure into this linear system, and what you get is the same frequency out, but you get a phase and amplitude change. And that's what this y hat and this v of y turns out to be. Okay, so that's how you get that kind of a structure. But the decomposition is performed in the moving frame, but this results in a time invariant system. And the reason is because effectively you say that x prime, you get rid of the time function over here by allowing x prime to be equal to x minus c of t, and so the traveling wave becomes in the x prime direction in this particular form. Okay, so so this becomes x prime rather than x minus ct, and so that's the underlining structure that we take. So the basic point then is what we want to do is find not V. Now we have VC. Now we want to find what the perturbation is. The perturbation is associated with this spectral decomposition and V hat. Now V hat is going to be related to a sum of these coefficients in time, as we had before, and we started, and the Chebyshev polynomials. But when you put this all together with the traveling wave, then what you get is basically, you put it all together with the traveling wave, what you get is a dynamic system which is of this particular form. So you have a dynamic system where the wave numbers are coupled together. Now, the pairs of three are coupled, but then this pair is coupled, this pair of three is coupled, and it goes all the way up and down. So the state space of coupling is large. And what we did is we cut it off at about 5. So the results I'll show you are basically a dynamical structure where we have a single wave number associated with the span-wise, but 5 associated with the stream-wise directions. So that's what we're looking at here. So the dynamical system basically is in the same form as we had it before, but in this larger structure. And for this time invariant system, we use linear quadratic regulator, but I mean, you can imagine the number of states that we had, so it was a little bit formidable. Okay, and then if you transformed it into the static frame, you get a periodic regulator. Okay, so this was the nice feature of it. So for a Reynolds number of about 5,000, this was the amplitude of about 0.03. what we had is, and all I'm going to do is flip through this quickly. The red line basically is if you don't do anything. So this is going into turbulence. The blue line is associated with a particular weighting on the controller, and the green line is another weighting. But you can see that we're killing off the instability by looking at the log of the energy. So this is for a wave number m equal to 2. These are all span-wise wave numbers, m equal to 2, m equal to 3. That didn't even get in there anymore, huh? M equal to 4, 5, and 6. So we stabilized this very complicated periodic system. So in conclusion, we looked at the Galerkin and Tau method, found out they were essentially the same because of the super damped eigenvalues in the Tau method. We were able to look at the reduced order, we reduced the order of these systems, and the transfer functions were similar, but the pseudospectrum changed dramatically. The low order LQG reduced things by about 17%. The upstream traveling wave reduced drag even further, okay, but has secondary instabilities. A time invariant linear system was used, which is coupled, but it was time invariant if we were in a moving coordinate frame. And the LQ controllers based on the time invariant system is determined that does suppress these things. And the bottom line of all of this is, well, it's in a static frame, it's a periodic controller. But the hope was, which we never quite finished, is, and we hope maybe in the future, is that a combination of traveling waves and associated controllers will eventually suppress turbulence.
Thank you.
I hope.